You know, you guys can come sit in the front. I see you shaking your head no. Okay, we're going to get started in just a second. So this is the second session of the day. I'm very interested to hear all these talks. I want to remind everybody that before lunch, we are going to all take a picture. So don't leave, and we're going to stick very carefully to the schedule to allow for time for the picture. And if you're in the overflow room, come down for the picture. So don't be late. Be in the picture. When the picture is shown 30 years from now, you want to be in it looking young and beautiful. Okay, so our first talk, luckily our first two speakers made it after all the travel difficulties that they had. So I'm very excited for this first talk by Yuichi Harikane of the University of Tokyo. And Yuichi, take it away.
Okay, can you hear me? Okay, good. So hello everyone, I am Yuichi Harikane from University of Tokyo. So first of all, I thank organizers for organizing this very nice conference, inviting me, and also changing schedule of my talk from Monday to Tuesday. Actually, my flight originally from Chicago to here was delayed a total of 26 hours. And also, my baggage is still in Chicago. But I am here, fortunately. Thank you. So I'm very happy to talk about galaxy formation with HWO. So in my talk, I try to explain that the HWO is excellent telescope not only for the exoplanet, but also for galaxy formation. So the one general question our human beings have is, where do we come from? So because we are living in the Earth, and the Earth in our Milky Way galaxies, if we want to understand where do we come from, we need to understand where our Milky Way galaxy come from and the other galaxies come from. And this middle figure shows the history of the universe. So left-hand side shows today's universe, and right-hand side shows the early universe. So after the Big Bang, the first stars and first galaxies form. Then these galaxies evolve through the cosmic time. Then finally, they became the galaxies in today's universe, like Milky Way galaxy, Andromeda galaxy, and other galaxies. Then in this context, we want to understand where do we come from, we want to understand how galaxies form and evolve in this 30.8 billion year cosmic history. So this is a galaxy formation study. And in the galaxy formation study, actually, we have many research topics, such as when the first stars and the first galaxies form, and how elements such as carbon, nitrogen, oxygen, all of them are necessary for habitable world. And we want to understand how these elements are produced in galaxies. Also in galaxies, gas consumed and recycled, so we want to understand how the gas is consumed and recycled in and around galaxies. And some people may be interested in the supermassive black holes, which is in the center of the galaxies. So we want to understand how the supermassive black holes form and evolve through the cosmic history. So this is a galaxy formation study. And we have a kind of the standard picture for galaxy formation. So this figure from JT 2017 nicely shows the current picture of the galaxy formation. So firstly, when galaxy forms, firstly the gas accretes onto the dark matter halo due to the gravitational potential, which is called gas inflow. Then the gas cools and stars forms, then galaxy forms. Then inside the galaxy, due to the nuclear fusion of the star in the stars, the metal enrichment occurs in galaxies. Then finally, due to the stellar wind or the supernova of the massive stars, which is the death of the massive stars, there is a gas outflow in galaxies. And this kind of the gas outflow suppresses the next star formation, which is called feedback processes. So this is a kind of standard picture of galaxy formation. So as you can see, the galaxy formation is a combination of a complicated baryon physics. So if we really want to constrain this kind of galaxy formation processes, we really need observations. And I think the HWO is a very powerful telescope to constrain the galaxy formation, because the HWO rest frame UV observations provide us rich information for galaxy formations. So this figure shows the HST COS spectra of the rest frame UV spectra of a local young galaxy. As you can see, we can see many emission lines and absorption lines, and these emission lines and absorption lines are useful to constrain galaxy formation processes such as chemical enrichment, gas inflow-outflow, and supermassive black holes. So in my talk, I try to explain that HWO is a powerful instrument by rest frame UV observations to constrain these galaxy formation processes. So I will highlight some of the sciences enabled by HWO. So firstly, I will talk about the galaxy scale sciences. And I think on Monday, Peter Senchina gave a nice talk about galaxy scale sciences from the perspective of the massive stars. But in my talk, I will talk about from different perspectives. So regarding galaxies, especially at high redshift, now JWST is very powerful, as you know. So this figure, this right figure shows the UV magnitude of the galaxy as a function of the redshift. And this gray data point shows the HST selected galaxies. And with its 3-year operation of the JWST, so this red diamond shows the JWST detected galaxies. So with its 3-year operation of the JWST, now JWST has discovered a surprisingly large number of galaxies up to redshift 14. So this is very amazing, and this really demonstrates the power of large space telescope. Then with such kind of very exciting discoveries with JWST, we are now finding a lot of new discoveries and a lot of new questions. And one of the big new mystery from JWST is, I think, nitrogen enhancement in galaxies. Okay, so this is a typical spectra of a bright galaxy at high redshift. So this is one of the most distant galaxy spectra at redshift 14 with UV magnitude of minus 20.8 magnitude. As you can see, there is a break around 1.2 micron, 1.9 micron, which is a break caused by the neutral hydrogen absorption in the intergalactic medium. But besides the spectral break, you cannot see any strong emission lines. So this is a typical spectra of a massive bright galaxies at high redshift. So then I show another example here. So the right panel shows another example of the bright galaxy at redshift 11, which is a very famous galaxy, GNZ11. As you can see, compared to the left one, you can now see a lot of strong emission lines in this spectra. So this really contrasts to the left galaxy spectra. So in this galaxy, we can see a strong emission line, many strong emission lines. And one of the notable emission lines is nitrogen 4 and nitrogen 3 emission lines, which are not usually seen in galaxy spectra. So this indicates that in this galaxy, there are a lot of nitrogen in this galaxy. Then if we calculate the abundance ratio of the nitrogen to oxygen as a function of the oxygen to hydrogen, then most of the galaxies follow the sequence. However, this galaxy GNZ11 shows about 10 times higher nitrogen abundance ratio compared to other galaxies. And then this is actually very surprising to us because nitrogen is usually very difficult to produce in the early universe. Okay, so in the left panel, I show the cumulative mass fraction of each element as a function of the time after the initial star formation. So different colors shows different element. So as you can see, oxygen increased very rapidly. So this is because oxygen is mainly produced by the quark supernova of massive stars, whose lifetime is very short, about 10 mega years. On the other hand, nitrogen, which is indicated by this green line, you can see that nitrogen gradually increases compared to the oxygen, because nitrogen is produced mainly by the stellar wind from AGB Roman stars or medium Roman stars. So the time scale of the nitrogen production is about 100 mega years. So as a result, most of the galaxies in the right, as shown in the right panel, follow the sequence. So that's why we are surprised to see the nitrogen-enhanced galaxies in the early universe. So then to explain this nitrogen-enhanced feature in the high redshift galaxies, we cannot explain this in the standard picture, so we need a kind of the new picture or new exotic pathways to quickly produce nitrogen in young galaxies, such as tidal disruption event, Wolf-Rayet stars, or supermassive stars. Then to understand which kind of process is responsible for the nitrogen enhancement, we really need theoretical efforts. And theoretical simulation actually predicts that such kind of nitrogen enhancement is occurred in a very, very small scale. So in the middle panel, this is a simulation result. If from the left to right, the times proceeds. And in the middle panel, I show the nitrogen over oxygen abundance ratio. So as you can see in this red panel, the nitrogen is enhanced in a small scale, which is about 50 parsec scale. So if we really want to understand where the nitrogen is produced and where is the nitrogen is enhanced in galaxy, we need to spatially resolve the elemental abundance ratio in galaxies. However, currently we are limited with spatial resolutions. So if we really want to spatially resolve galaxy, we need to go to local universe. Then there is some example of the nitrogen enhanced galaxies in the local universe. So this is one galaxy, MRK 996, so which is a local young galaxy. In the right panel, I compare the spectra of this galaxy and GNZ11. So as you can see, the nitrogen 3 emission line is strong compared to GNZ11. So this is a nitrogen enhanced galaxy similar to high redshift ones. However, this is a HST cos spectra, so this is aperture integrated spectra. So we know that this is a nitrogen enhancement galaxy, but we don't know in which part of galaxy nitrogen is enhanced. So that's why we need HWO. So with HWO, thanks to the large mirror, we can draw the spatial map, or HWO can spatially resolve the elemental abundance ratio by conducting the spectroscopy with MOS or IFU with 40 parsec scale through the rest frame UV emission lines. So currently we only have the galactic integrated spectra, but with HWO we can resolve the elemental abundance ratio in the galaxy. Then I think we can investigate the origin of the mysterious nitrogen enhancement in young galaxies. So then we can tackle the new big mystery from JWST with HWO. So then with HWO, I think we can fully trace the chemical enrichment in galaxies. Then there is also another interesting science cases if we go to a much, much larger scale. Then if we go to a larger scale outer than galaxies, then one big theme is the galactic ecosystem. So we need to understand how the gas is consumed and recycled in and around galaxies. So this is a kind of the high priority theme in galaxy formation studies defined by Astro 2020 decadal survey. So to constrain this kind of baryon physics, we need to trace the kinematics of gas in and around galaxies. And rest frame UV is very strong in this context, because a Lyme alpha rest frame UV hydrogen Lyme alpha emission line is a resonance line whose line profile is significantly affected by the gas kinematics. So I show two examples of the outflow case and inflow case. So we usually observe Lyme alpha photons that are scattered from the gas. So in the outflow case, because the gas is outflowing towards our galaxies, then the Lyme alpha photons we observed is a scattered photons from the outflowing gas. Then that's why we see the Lyme alpha photons are red shifted, and that's why we see that Lyme alpha photons is red dominated if the gas is outflowing. On the other hand, if the gas is inflowing, then because the Lyme alpha photons we observe is blue shifted, then that's why the Lyme alpha emission line profile is blue dominated. Okay, then by investigating the Lyme alpha line profile, then we can infer the gas kinematics in and around galaxies. So then this is a simulation result of the gas kinematics around galaxies. So blue and red shows the inflow and outflowing gas. Then if we observe the Lyme alpha emission line in each of the positions, then we can say that, oh, this gas is outflowing and this gas is inflowing. And however, currently we are limited by the spatial resolution and the sensitivity. So this is an example of the current observation for a galaxy from Keck telescope. So the blue and red color shows the Lyman alpha blue and red flux ratio. So as you can see, in the outer region of the galaxy, there is a kind of a blue pixels, so which indicates that there is a inflow gas around galaxies. However, we are limited with the current sensitivity and spatial resolutions. And I think with HWO, we can fully trace the gas kinematics in and around galaxies in much outer scale. I think up to 40 kiloparsec. Then we can directly see this kind of the picture of the inflowing gas and outflowing gas. Then we can directly test this picture of the standard galaxy formation picture. So this is a kind of very exciting. So and I think only HW can test this picture of galaxy formation. Then finally, I want to go to a much smaller scale, go back to smaller scale, but much smaller scale than galaxies. I also want to talk about supermassive black holes. So you know that the supermassive black hole is a very massive black hole whose mass is about 10 to 6 to 10 to 10 solar mass. And the supermassive black hole is residing in the center of the galaxies, including our Milky Way galaxy. So this is a picture of a black hole shadow in our Milky Way taken by Event Horizon Telescope. So we know that there are supermassive black holes in the local universe. However, we don't know how this kind of supermassive black holes form and evolve in the universe. So this again shows a history of the universe. And a supermassive black hole may form in the early universe as a seed, and these seeds grows through the cosmic time. Then finally, they became the supermassive black holes in today's universe. However, we don't know what kind of seeds are made, and also how these seeds grow to the supermassive black holes. Especially regarding the seeds, there are two scenarios. One is a light seed, whose mass is about 10 to 100 solar mass, which is probably remnants of the first stars. And the other one is a heavy seed, whose mass is about 10 to 5 to 10 to 6 solar mass, which is made by direct collapse of the gas. So to understand the origin of the supermassive black hole, we need observations. And actually nowadays, JWST is also finding the early supermassive black holes. So we didn't expect before the launch of JWST, but now JWST is finding a lot of supermassive galaxies with supermassive black holes as active galactic nuclei, AGNs. So this picture shows one of the examples of the supermassive black hole galaxies with supermassive black holes found by JWST. And by spectroscopy, we can also measure the black hole mass. So this right panel compares the supermassive black hole mass as a function of the galaxy's stellar mass. And this red and magenta symbol shows supermassive black holes found by JWST. So with JWST, we are now reaching to the mass regime of about 10 to 6 solar mass in black hole mass. So this is very exciting. However, if we really want to understand the origin of the supermassive black holes, we need to go to much lower scale, a lower mass scale, because the seed of the black hole mass are expected to be about 10 to 4th or 10 to 5th. And I think HW can also search for such kind of the massive black holes down to 10 to 4th solar mass. So by spatially resolve the kinematics of the velocity, the velocity field of nearby dwarf galaxies. Actually, such kind of the studies are already done in local galaxies. So here in the left panel, I show the example of the velocity field of a galaxy of massive galaxy. So y-axis shows the velocity field and x-axis shows the radius. You can see the high velocity in the center of the galaxy. So this is due to the gravitational potential of the massive black holes. So by observing this kind of the velocity field, by spatially resolving the gas kinematics or stellar kinematics of galaxy, we can infer the black hole mass of the center in the center of the galaxies. However, currently this kind of study can be done only in the massive galaxies due to the sensitivity and the spatial resolution limitations. However, with JWST, we can go much to a lower mass scale by observing this, conducting this analysis with dwarf galaxies. So this is a figure from Pak-Chiu et al. So black hole mass stellar mass relation, and with HWO, we can reach to the mass regime about 10 to 4th to 10 to 5th solar mass. So which is a kind of mass regime of heavy seed. So I think with HWO, we can search for the massive black holes down to 10 to 4th solar mass. Then we can understand the origin of the mysterious supermassive black holes in our universe. So then this is a summary of my talk. So I highlighted 3 science cases that HWO can allow us to conduct in the larger scale. We can directly test the standard picture of a galaxy formation through investigating the gas kinematics by detecting inflow and outflow in and around galaxies. And in galaxy scale, I think we can fully trace the chemical evolution and investigate where the nitrogen is produced and enhanced, which is a kind of the new big mystery from GSFC. And much smaller scale regarding the supermassive black holes, we can search for the massive black holes down to 10 to 4th solar mass, and we can investigate the origin of the supermassive black holes. So I think HW allows us to conduct transformative science researches on galaxy formation thanks to its high sensitivity and resolution in UV. So I think HW is a kind of crucial final push for galaxy formation studies after GSFC. And all of the science cases I highlighted here can only be accomplished with HW. Okay, thank you very much.
Okay, we have time for some questions.
Hi, I'm Thais Stork-Bergman from Brazil. Very nice talk. I wonder which is your favorite indicative of the mass of the black hole. Because, you know, we have the kinematics, but, you know, the kinematics, as you mentioned, can be inflows, outflows. So how can you constrain the mass of the black hole? Usually people use the width of the line, but, you know, I would like to know your opinion about that.
Yes, a good point. Thank you very much. So I think the kinematics information is much stronger and much direct than the broad line method that we usually use in GSFC, because in the broad line measurement, we need to assume the local relation. But such kind of local relation can be calibrated with the kinematics information. Of course, there is an inflow and outflow activity, but there is a kind of outer scale. But we want to from much smaller scale, which are purely affected by the gravitational potential of the supermassive black holes. So I think in this sense, HWO studies with kinematics to search for the black hole is much more direct than GSFC, I think.
Okay, thank you.
Hi, Nancy Levinson, Space Telescope Science Institute. With the nitrogen enhancement and considering the models, it looked like there wasn't only the spatial concentration, but there was also a temporal effect that changes over time. And so I was wondering if you could comment on some of the prospects for accounting for that kind of variation.
Yeah, that's also a good point. Thank you very much. So as you mentioned, yeah, this is a kind of, I think, temporal feature. So because if the time proceeds, then there is a supernova which produces massive oxygens. That's why the nitrogen is diluted by oxygen. So then nitrogen to oxygen abundance ratio significantly decreases. So in that sense, we may looking at a very special phase in galaxy formation, or maybe we are missing some of the physics which enhance the nitrogen. Currently, we don't know. That's why we need observations.
I was just curious what spatial and spectral resolution you'd be looking for from HWO for this integral field measurement.
Yeah, thank you. So regarding the spatial resolution, we want to conduct a 40 parsec spatial resolution in nearby galaxies. And regarding the spectral resolution, actually we don't need a very high spectral resolution. Maybe about 10,000 or about 1,000 is enough. We can just want to resolve the emission lines.
All right, thank you so much. I'm glad you made it.
Thank you.
So our next speaker, Shivani Shah from North Carolina State, who also braved treacherous roads and floods to get here. Thank you so much.
Can you hear me? Can you hear me? Okay, awesome. Oh,
My failed in one of my...
Okay, awesome. We'll make this a little bit interactive. If you are wearing gold, platinum, or silver, even if it's a coating on your jewelry, please raise your hand. Whoa! I was afraid nobody was wearing it. Okay, these precious metals are such a significant part of our everyday lives, and yet we do not know how these elements are built up over cosmic time in our universe. And part of the reason is that we haven't observed these elements all that much in the universe, but with the ultraviolet spectroscopic capabilities of HWO, we will be able to change this. So these elements are part of a group of elements called the neutron capture elements. These elements are heavier than iron, and they're created by captures of neutrons instead of typical fusion processes. So aside from these precious metals, we also have elements that have medical and technological applications here on Earth. Some familiar names might be mercury, lead, tin. This group of elements also consists of elements that have supported life and habitability on Earth. So for instance, iodine is an essential mineral for biological functioning, not only for humans, but invertebrates, algae, and bacteria. It's literally in our food. This group also consists of thorium and uranium. These elements are radioactive, and they contribute to up to 30% of the Earth's internal heat budget. And this internal heat helps maintain water cycle, volcanic activity, and the magnetic field around the Earth. In fact, a simulation study from 2020 suggested that an optimal amount of thorium and uranium would be needed in exoplanets to maintain habitability. Too much of these elements, and then the magnetic field would not be sustained, and too little, and the planets would be geologically dead. So in spite of the impact of these elements and the significant portion of the periodic table that they take, we really don't know where these elements are primarily created. Our current candidates for where these elements are created in the universe are exotic type of supernovae, mergers of neutron stars or neutron star black holes, and even explosions on the surface of neutron stars. But to observe these events live in action is very, very difficult. These are rare, these are faint, and Erika is leading such a great effort for HWO to be able to do this. But even if we do observe these events in real action, it is nearly impossible to obtain detailed information about the elements that were created and the amounts in which these elements are created. A more successful technique is using stars as time machines. So after an enrichment event occurs, it's going to deposit these freshly created elements in the surrounding interstellar medium. And then the next generation of stars will form, capturing these chemical signatures in their atmospheres. Now, these stars will live on for billions of years, and then we can point our best telescopes towards these stars, collect stellar spectra, and we get a wealth of information about the elements that were created in these events and the amounts in which these elements were created. Now, because these elements have different atomic numbers, nuclear structures, they each uniquely trace a different property, nuclear and astrophysical property of these enrichment events. So to build a full picture of what type of enrichment events are creating these elements and how these enrichment events are working, we want to be able to observe as many elements as possible in as many stars as possible. So where are we at observationally right now? For all of these green elements, we have abundances for these elements in way over 1,000 stars, almost 10,000 stars in some cases. We know how these elements are being built up very well now. For these light green cases, we also have a substantial amount of data. We have abundances in over 100 stars. And all of these abundances are courtesy of ground-based spectroscopic surveys, individual efforts as well. Then we have these orange elements for which we have abundances in tens of stars. And then we have these red elements for which we have abundances in less than 10 stars in the entire universe. And the bottleneck is that most of these elements require ultraviolet wavelength coverage. Their strongest absorption lines are in the UV. And by number, this is about 30% of neutron capture elements that require UV wavelength coverage. So in that respect, the Hubble Space Telescope has been a pioneer with 2.4 meters. It had a decently high resolution spectrograph in the near UV and far UV wavelength ranges. And it really showed us what type of science we can do by observing these stars and collecting data on these elements. For instance, it has led to the determination of gold abundance in 7 stars. And here I'm showing the spectra from Hubble from these, it's only 6 stars here, and the best fitting models that we have. These are the only 7 stars for which we have gold abundance in the entire universe aside from the sun. Similarly, for platinum, it has led to the abundance determination of platinum in about 10 stars. And here I'm showing 3 of these absorption lines from 3 different stars. It has also led to the most extensive chemical inventory of any object outside of the solar system. And this was for a metal-poor star called HD 222925. And the study was led by the fantastic Ian Roeder, who's sitting here. And he was able to determine abundance for 42 neutron capture elements. And you will see all the elements in blue. Those are the elements for which abundances were determined exclusively with HST due to its UV capabilities. And the elements in green, for that, HST helped improve accuracy as well as precision in abundances. Now, we love this type of extensive chemical inventory. It provides very good constraints on the nuclear and astrophysical properties of the enrichment events that are creating these elements. The problem is we have less than 10 stars with both UV and optical spectroscopy in this manner done. And the reason is because HST is relatively small, with 2.4 meters. Its spectrograph sensitivity goes out only to the solar neighborhood, which is about 1 kiloparsec for giant stars, even less for dwarf stars. And for the type of science we want to do, there are not many stars available in this region, so there's only tens of stars that we could do science with. But this is where the Habitable Worlds Observatory will really, really revolutionize. With 6 to 8 meter mirror is going to open up the entire galaxy for us. The sensitivity will go out to 20 kiloparsec. We'll have hundreds to thousands of stars. We already have hundreds of thousands stars identified with which we can do this science. So we're going orders of magnitude higher. We will require a high-resolution spectrograph, at least 40,000, ideally 100,000. I will endorse 100,000. Wavelength coverage, again, near UV, down to 1,500 angstrom. And I love this quote from Ian, which is, HW could observe the UV spectrum of nearly any star whose optical spectrum is accessible from the ground today, which is just fantastic. And this is the vision of HWO. So here we have europium on the left side. It is the most well-studied neutron capture element. Its abundance has been determined in almost 10,000 stars. We know how this element builds up from the most pristine metal-poor conditions to very metal-rich conditions like the solar. We know how this element rises through cosmic time. Then we have thorium. It is one of the heaviest naturally occurring element in the universe with a very weak absorption line. And even for that, we now have abundances for over 100 stars, and we're starting to create this picture of how thorium built up over cosmic time. And both of these element abundances have been determined with ground-based optical surveys and individual studies. And this is the kind of picture HWO will bring to us for 30% more elements, for 20 more elements, like gold, platinum, lead. We'll have iodine, cadmium, arsenic. It is going to be fantastic. And with that, I'm going to leave up my summary slide, and I'll let you know there is a white paper by Ian Roeder and Rana Ezzedine on archive just on this topic, and you can take a look for more information. Thank you.
questions for Shivani? So I'll start off while you guys are thinking of your questions. Your comment about the thorium and uranium kind of amounts made me think of the talk earlier this morning, which was about like which stars we're looking for habitable planets. So is there any overlap between that catalog of stars and the ones that, I mean, it doesn't seem like there's any uranium measurements?
Yeah, uranium is very difficult. We don't have uranium measurement photospherically even in our sun. It's just the line is very weak. So we have maybe I think there's 7 or 8 stars now. Thorium has been done for solar twins. It's been done in the disk now. So it's been done for the metal-rich stars. There's this recent study that did thorium in the Kepler field. So please take a look at it. And I think that will, I don't know if there's an overlap between that study and what the working group is working on, but it might be worth taking a look there to see what they have. But yeah, that would be one way to
Get a good Earth.
classify stars that are, good targets.
Other questions? We have one up in the front.
Great talk. Thank you. Mark Postman here, Space Telescope, Science Institute. For these 100 to 1,000 stars we want to get with HabWorlds, do you have a need to do it in different environments, or can we, if we have a multi-object spectrograph, if you got 50 in one cluster and 50 in another, would that be enough, or would you really want to spread out over different environments?
We want to spread out for sure. So we definitely want clusters too. That would be nice. But we want to do different parts of the halo because the reason is that we will, for the metal regime, we will mostly be looking into the halo. And these stars are probably coming from different accreted events. So going into different regimes will take us to different dwarf galaxies that were created, clusters that were created. We can do the streams. So for streams and clusters, we can do multi-object, probably. Yeah, that would be nice. But yeah, different parts as well. Also, we can try to get more metal-rich stars in the disk, solar neighborhood. So, yeah.
Any other questions? All right, thank you so much. Do you have a
Testing? Testing?
Nope.
Hello?
All right, our next talk is Chris Carr.
Or Cody Carr, sorry. No worries. Well, first I'd like to start off by thanking the organizers for putting this awesome conference together and giving me the opportunity to represent my SCDD group, my various team members here. Our work concerns the epoch of reionization, which represents a time period in the early universe when the first galaxies reionize the majority of hydrogen-filling intergalactic space. So many fundamental questions about the epoch of reionization remain open. For example, we still don't know what the primary sources of reionization are or how reionization evolved over time. To answer these questions, ideally what we would like to do is measure the amount of ionizing radiation emitted from individual galaxies. So what this amounts to is measuring its intrinsic production times the escape fraction, which is the amount of gas that the amount of photons that actually escape from the surrounding circumgalactic medium to ionize intergalactic space. Unfortunately, the ionizing photons are lost upon ionizing the surrounding gas, so we can't actually measure this directly. So what we do is we rely on indirect diagnostics of Lyman continuum escape, which are typically established in the local universe. So for example, how this works is JWST will observe a high redshift galaxy, which we see here, and then we take an escape diagnostic. For example, in this case, it's the far ultraviolet continuum slope. And then we feed that into a a locally established empirical relation to predict the escape fraction. So there's still a lot to be desired with this overall process. For example, many of these relationships show a large degree of uncertainty. We'd also like to develop a better physical understanding to do among other things, establish how well this relationship would evolve with redshift. So I'm showing another diagnostic here, the O3-O2 ratio versus the UV slope. So the O2-O3 ratio, or O3-O2 ratio is typically a measure of the amount of ionizing photons, while the UV slope is age and dust. But this, and then over here we have the escape fraction shown in color, and these are galaxies taken from the LOSI Lyman Continuum survey, which is the largest local study of Lyman Continuum leakers to date. And I want to draw your attention to the large amount of scatter, which appears in the center of this picture. And I claim that this is largely dependent on the anisotropy of the escape. So on the right here, I'm showing one of the few examples that we can check on Lyman Continuum, or spatially resolved Lyman Continuum escape in the sunburst arc galaxy. So on the same plot, we're showing different spatial regions, so strong leaking regions in black, and then non-leaking regions in red. And then the global galaxy measurement from integrated spectra was shown here in purple. And we can see a lot of this information is lost among spatial averaging. So the takeaway message is we need to spatially resolve Lyman Continuum escape to understand what's happening. So this is easier said than done, and that's primarily due to the large scales involved. So at the fundamental level, we want to resolve Lyman Continuum escape on the scale of superstar clusters, which range from about 1 to 100 parsecs. And then we want to study the escape all the way out from the CGM, which we've heard can extend beyond the virial radius or even greater than 100 kiloparsecs. So what really influences the Lyman Continuum escape is the column density of hydrogen and gas hydrogen and dust along a given line of sight. So this is showing results from a simulation where these distributions are for the column density of hydrogen along many different lines of sight by Jennings et al. And we can see here there are estimates from integrated spectra shown here in red. And we see a bias between the different distributions, which they attribute to the differences between spatial inhomogeneities and also resolution effect. So again, the takeaway message is to understand the gas distribution affecting the escape, we need spatially resolved spectra. And then finally, to understand the physics behind Lyman Continuum escape, we need to understand how feedback influences the amount of hydrogen and gas along the line of sight. So there are usually 3 scenarios that are considered. So for example, radiation feedback, ionization pressure can both evacuate low-density channels, which will allow Lyman Continuum escape. Also, another possibility is supernova. So supernova can drive large-scale galactic winds, which can remove gas from a galaxy to open up channels for Lyman Continuum escape. And they can also work in tandem. So this has been proposed in what's usually called a 2-stage burst scenario, where the supernova clear the densest gas and then radiation can finish it off. All right, so we're interested in a bunch of various quantities to start understanding these different properties. So for example, with the outflows, we want to understand how much mass, momentum, and energy they transfer through their environments. We want to know the velocity dispersion, column densities, as I've mentioned. The ages of stellar populations are very important in this work for identifying the different types of feedback. For example, very young stars, possibly less than 3 megayears, it would be unlikely for them to have supernova. So that would be an indicator of strong radiation and stellar wind feedback. And then, of course, I've listed some of the different diagnostics for Lyman escape here. Oh, I'm sorry. So as we've seen, the UV offers us an abundance of different lines for probing this information. So I've listed here some of the low ionization state lines and warm ionization state lines we're interested in. This will roughly span a temperature scale of cold gas from about 10 to the 2 Kelvin all the way up to 10 to the 6, which is going to be probed by our oxygen 6 line here around 1032 angstroms. So in summary, our rest frame, we're thinking about roughly 700 to 1800 angstroms for this science. So what can we do currently? So this is showing two different spectra of the same galaxy. So this was taken with a Hubble Space Telescope, the COS spectrograph. And on the left here, I'm showing a low resolution spectrum versus the medium resolution grading. So the left is what's typical for Lyman continuum escaping galaxies. This is from the low-Z Lyman continuum survey. And then the right was a different study. But what I want to point out to you is that the inferred escape fraction from these would be very different. So the residual flux here on the bottom of the absorption well is typically associated with the amount of gas along the line of sight, the covering fraction. So we can see that with the instrumental smoothing, the value can change dramatically between the low and high resolution state. So this can affect what we'd infer the escape fraction is. So this is showing why we need such high resolution spectra. So so this comes at a cost, however. So I did some calculations for HST. So for a galaxy here, a strong leaker of about 13% at redshift 3.5, get a signal to noise of 10, resolution about 30 kilometers per second. It would take us about 27 hours or 30 orbits. So that's very expensive to get this data with our current technology. However, with HWO, with a larger aperture, this would reduce this down to about 48 to 27 minutes for the 6 to 8 meter apertures, respectively. So with the new telescope, these types of observations would become commonplace. So I had to throw this in here, but this is a new observation I've recently got with my team. So this is showing the Lyman alpha spectrum at medium resolution, taken with COS again. So I think this is like one of only 6 of these that I know of in existence. But what I wanted to point out to you is that as we're looking in the high resolution at the galactic winds here emerging, you can actually start to see multiple components forming. So if we go down to the lower optical depth line, you can see what we call the wind component here, and then the component centered on the transition line, which we usually refer to motion or occurring from motion in the ISM. And the point is, at high resolution, we'll be able to start to see different components. So the point is that, high resolution spectroscopy isn't just going to, reduce the uncertainties on quantities we already know. We're going to be able to discover new components and constrain different parts of models. So there's opportunity for discovery at high resolution. And of course, to do the transformational science, as we've heard a lot of, we need to get the spatially resolved spectra. So this is showing a spectrally imaged galaxy by Burchett et al. Using KCWI. So in this scenario, each of these spectra correspond to a different spatial region. And this will be great for the modeling of galactic winds. This will allow us to, or knowing the spatial distribution will allow us to break a lot of degeneracy in these models. And of course, with HWO, what we want to do is increase the resolution so we can take this all the way down to the superstar clusters. So we'll be able to pinpoint exactly where the feedback is coming from. So I also calculated some of the numbers for you here. So at a redshift about 0.22, which is about the sweet spot for measuring Lyman continuum, we're going to need diffraction limited observations about 4.6, 3.5 milliarc seconds, which would give us a physical scale of about 16 to 12 parsecs for the 2 different aperture sizes. I should also mention we need a fairly large field of view to do this. So we're thinking of at least 3 arcsecond aperture. So at this spatial scale, this would allow us to see about 10 kiloparsecs. But if we want to constrain the entire CGM, as we mentioned, the full extent to the winds, we'd want to go higher, probably 5 or 10 arcseconds. Okay, so I'll leave you with a brief summary here, looking at the different qualifications we're looking for to do our research. I'm happy to take any questions.
Any questions? Okay, we have one in the front. Thank you.
So your summary slide, Jane Rigby, NASA Goddard Space Flight Center. Your summary slide lists a wavelength range that goes down to 950 angstroms, but I think in your talk you mentioned going down to 700. So could you talk about what's between 700 and 950 that we might care about and how important it is?
Yeah, I might have been in a rest or observed frame there, but there is an important feature below the 900 angstrom. So there's this idea of the Lyman continuum bump, where, for example, free electrons might combine with atoms and give us the hydrogen to give us a lower wavelength feature. So people are interested in this in Lyman continuum escape because it can influence the values that we measure. So yeah, it's the Lyman bump. Yeah. So this, so this is sort of taking into account a sweet spot in the redshifts, but yeah.
Another question from Kevin.
Thanks. Nice talk, Kevin France, University of Colorado. So I'm sorry if you said this and I missed it, but could you describe again the range of resolutions that we're talking about? Like, do we need, for these very, very high angular resolutions, do you require the very, very high spectral resolutions at the same time? Or what is represented by the range of spectral resolutions you're asking for here?
Yeah, so I sort of put the full range that I would consider to study the galactic winds. So I would consider this our lower end to really get a much better constraint, as I was showing you in the picture. To get the higher end constraint of about 100, so what that's corresponding to is the resolution of the turbulent and thermal motion in the outflows, or in the cold clouds in the outflows. So I put that as an upper limit, as sort of representing, the highest resolution, which I think we could discern actual kinematic information in the lines and the winds. So it's essentially the highest value I think we should go to. Past that, we can't really get any more information from winds in this way.
Okay, we have a question. Oh, you don't have a question? Oh, same question. Okay, any other questions or anyone online? There's one online we'll go to.
I have a question from Ethan to say what he says in total. We have now seen several talks that appear to motivate the science case for a far UV instrument aboard HWO. What are the obstacles, alternatives, or instrument parameters that members of the community should be thinking about when it comes to such a FUV capability?
What instruments should we be considering?
What are the obstacles or challenges?
Obstacles, alternatives, or instrument parameters?
I mean, I'm not an instrumentalist. I'm not sure if there's too many obstacles because we already have some, we already have instruments that can observe this range.
It's a question of codings.
Yeah, I'm not. If anyone else
Yeah.
wants to take that.
We'll have some instrument experts coming. Yeah.
Can I just for a
Yes.
second?
Just introduce yourself though, because you did it before.
Oh my God, I'm so sorry. That's so embarrassing. Hi, I'm Sarah Tuttle from the University of Washington. I will post it in the Slack, but we have a UV technology white paper that reviews both some of the motivating science cases for the FUV, as well as the challenges, but a broad range of technologies that will help us meet the requirements for various science cases.
All right. So we're going to go to our next talk. Thank you, Cody.
Check, check. Is this on? Not on. Oh boy.
Right.
Now it's on.
We have Brian Fleming from the University of Colorado.
Hey everybody, thank you. As introduced, I'm Brian Fleming. And I was invited here to give a talk on integral field spectroscopy for the far UV on Habitable worlds. And I was very excited to give this talk. It was going to be a great sales pitch. I was going to come here and convince you all, and Lee and everybody, how cool this was going to be. And then yesterday, apparently it's already in. So I made some new slides. And while my previous talk was going to make you all very excited, unfortunately, I think this one might make some of you kind of sad. So I'm sad. Anyway, so I'm gonna give a little overview of why we're talking about integral field spectroscopy on Habitable worlds when we didn't on LUVOIR and HabEx and those studies. And then we'll move from there into a little bit of what might it look like? What are the pressure points for design range? I mean, anything's possible, but where does it start to get hard and where is it easy? and we'll leave you with that. But I'm going to start with a little bit of a backstory. So like many people here, I did a thesis when I was a grad student. It's not important what I did it on, but there was some Hubble data, and then I needed some optical data. Specifically, I needed spectral line maps in a bunch of star-forming galaxies. Interestingly enough, Cody showed a picture of 2 of them, so that was cool. And I did this by going to a 3.5-meter telescope in New Mexico and spending 51 nights moving a long slit across the galaxy, integrating and moving it again and integrating. And it was great, and we made great data products, and data cubes are fun. Then a friend of mine came to Space Telescope and gave a little lunch talk, and she was basically doing the same thing, except she went to the VLT and used an IFU. And I asked her at the end of her talk, I said, well, how long did it take you to get that data? And she said, oh, it took forever. I mean, it was like an hour and a half per galaxy. I could only do a couple a night. And so since then, I've been a little obsessed with this. And it's kind of like, the life quest to get efficient, extended object spectroscopy into space, especially for the ultraviolet. I've met some like-minded people along the way, and now, all of a sudden, and this wasn't the case when the LUBAR and HAVEC studies were being done, there are instruments and designs, mostly suborbital, but that's where you start. It's a great program, to really push these integral field concepts into something we can put into space and put in the ultraviolet. Okay, so I mentioned this is kind of new, so let's review a little bit the state of the art. Everything we've ever really had before has been pretty much like COS or FUSE or IUE, and they're designed to look at point sources. They're designed to look at stars, or they're designed to look at quasars, and when you put them over an extended object, they give you one little snapshot view into there. So not particularly efficient when you start talking about big diffuse structures. Now we do have STIS, and there was another mission called SPEAR, which has a long slit, which allows you to maybe do the type of thing I did as a grad student, but not particularly efficiently, although there's some posters where they've started doing this recently, which are really cool. But of course, STIS doesn't get to Oxygen 6. It doesn't get down into the real Lyman UV. It's a pretty small field of view. SPEAR is a very large field of view. So we haven't really been able to effectively look at extended objects as extended objects. We tend to look at them with point source spectrographs and infer, oh, we looked at this part of a galaxy, ergo the whole galaxy is like this. It's not the way it is. And the reason why is because UV technology was always really hard. But things have changed, thanks to investments, especially investments driven by the concept studies and this project here. We now have much better mirror coating, so you can actually put more than 2 optics in a system and actually get photons out the other side, which is amazing. We have large detectors, which is really important when you want to get a lot of spectra at once. That's actually the most important parameter. How much detector area you have equals how much science you can collect. That's what it gets down to. And so because this has changed, we're now ready to do different things. So the thing we've been talking about up till now is the multi-object spectrograph, which is essentially a long slit that you can chop up. And you can chop up the different chunks and move them a little bit to the left or a little bit to the right. But you can't move them anywhere you want. You're limited to about 1 object per row of whatever your multiplexing device is. So these 2, for instance, would be illegal. Any light getting through that would overlap with light from another aperture. You get confused. It doesn't do anything for you. So this is wonderful if you have a star field or a galaxy cluster and you want to look at a bunch of discrete objects. But when you start looking at an actual diffuse source, like a galaxy or a cloud, it takes the exact same amount of time to completely cover this structure as it does with a long slit. And so this is a real limitation when we start talking about some of the things that have been presented in many of the talks so far. So what we want is this. We want to be able to just throw a bunch of apertures over there and get a spectrum from each one at a time. And so you can make a data cube where you essentially can have an image of your target, but at every wavelength in your bandpass. Okay, so how are we going to do that? There's a lot of integral field spectrographs on the ground. So the first thing you do is you look at all of those designs and you pick which ones can work. There actually has been a UV IFU. The Fireball balloon was a UV IFU in the near UV using fiber optics. Unfortunately, that doesn't really extend into the far ultraviolet, and neither do a lot of the other techniques like lenslets or things of that kind. So the way that we've settled on after lots of years of looking at it is the image slicer, which is what Muse is or KCWI or many other projects. And this is an all-reflective version. So on a standard long slit, you put light through a slit, it transmits it through to a grating, the slit defines your field of view, and you disperse your light and you get a spectrogram with 1 dimension of spatial information and then spectral For an image slicer, you replace that transmissive slit with a series of reflective mirrors that are slit-shaped, each one angled slightly differently to take its slice of the field of view to a different location. And then typically on the ground, you'll have about 25 other optics that will rearrange that light and put it on the detector in a way where things don't overlap. But in space, we can't do that, and we certainly can't do that in the far UV. So we came up with a sort of more space-friendly design where we take those 25-ish optics and we condense them down into one really complex grating per slice. So now you have an array of gratings on the order of 20 to 50 to 100, depending on how many you want. Each one designed to correct for aberrations, disperse the light, refocus it, do all that stuff in one go. Okay, so the first one of these that we built is called Infuse. It's a sounding rocket. It's student-led, low budget, but even low budget, it's got a detector that's just about what would meet the Hab Worlds requirements. It's got an image slicer that's just about what we need for Hab Worlds. It's got 26 gratings, all of them just as good as the ones on COS. Well, I mean, those went through quality assurance, and ours didn't really go through quality assurance, but same type, okay? And this works. It's launched, it's done science in space, but the lab data is a little more compelling. So on the top right there, basically we defocused far UV light in a collimator, and it spread out over a couple slices, so you see a few spectra. You zoom in on the Lyman alpha in each one of those, and that's shown down there. And then you just, put them where they're supposed to go, and you recreate the donut. And galaxies are donuts, so there you go. Okay, so that's great. Now, how does this port to habitable worlds? And the answer is, it seems like it would just kind of port directly. So let's talk a little bit about what that might look like. But first, we're going to start with some cartoons of what the limitations are and the challenges. So first off, these IFUs look magical. Okay? They're so wonderful. You get all this big spatial information. We're going to have giant fields of views and lots of stuff. But the truth is, you don't actually get any more spectra than you get with a long slit. So a long slit is typically designed where you have a detector of a certain size, and you fill it with spectra, and the height of your slit defines that is by the height of the detector and how much light you can put on it. When you do an IFU, what you essentially do is you chop up that slit, just like the MOS, but now you're moving it into a rectangular shape. But the detector size, if it's the same, still gives you the same number of spectra. So you're taking the same field of view, you're just making it into a more favorable shape for looking at an extended source than the long slit, which gives you that long cut. Okay, so as a toy model, and don't take any of these numbers home, this is not like what Hab Worlds would be limited to. If you take the same detector we have in Infuse, just 100 by 100 millimeters, you throw a reasonable PSF spot across that of maybe 50 microns. I know you can do better, but this is two-dimensional field aberration control. It's a little harder than one dimension in a long slit, so on average, the spots will get a little fuzzy in some areas and a little better in others. That's going to give you about 2,000 spectra you can cram on this detector, going all the way across. So if you want 100 milliarc second resolution, which is going to make a lot of you sad, then you'll get maybe a 4.5 by 4.5 arc second field of view, which will also make a lot of you sad. Oops. And of course, if you want to get better resolution, the field of view just gets smaller and smaller and smaller. So the key to this is lots of detectors. Or maybe you get a little creative and do something else. So let's get into that. So this is just showing that. I think you all got it, but if you make your resolution better, then your field of view goes down. I think it makes sense. So there's a lot of projects that have gotten very excited about this. It's also going on in planetary science. So this is a thing led by Amanda Hendricks from Planetary Science Institute, where we're basically taking the infused design and replacing the image slicer with a MEMS mechanism. So this is a series of mirrors that are individually actuatable. And I wouldn't have normally talked about this until I found out that now, the IFS is in, so maybe we'll think about it. And the reason for this project is, especially in planetary science, they want a very large field of regard. So you want to be able to look at a lot of targets. But your detector area still limits the number of spectra you can get. And so what this is essentially a hybridized MOS IFU, where you get over the limitations of the MOS. You can put two apertures next to each other. But you can't cover your whole field of view because you run out of detector space. But it allows you to go into, say, a galaxy cluster and find 4 galaxies and build little IFU apertures around each one, maybe a little bit in between, and throw out the stuff you don't want. So this is one thing that if it was developed, and this demonstration will probably happen in 2027 in the lab, could provide us a way around this problem where you have a large available field of view, but only so many spectra you can pack But let's not talk about that too much. Let's just talk about what we could do. So the other problem we have is these are like, the MOS is going to have a lot of different modes, right? It's going to be like STIS. It's going to have 8 different grading modes. It's going to extend into the visible. It's going to have NUV. It might have imaging capability. It's going to do all sorts of things. It's going to be really the instrument that you go to for whatever you want, different resolutions, et cetera. When you start talking about an IFU, it gets a little more complicated, especially if we go with this kind of design where you might have 50 gratings in an array, and then you want to put those on a turret with another 50 gratings and another 50 gratings. It's possible, but it does make it a little bit more complex. And so there's a lot of different ways around that, and I'm not going to go over all of them. Some of them are being prototyped. But basically, we have a range of options available. We can go with the ultimate option, which is where you do have a bunch of turrets, and you're changing in image slicers and changing in field of views and putting different resolution gratings in there. Or we can say, hey, you know what, this is a supporting instrument to the MOS. The MOS is the one we want to put all of our effort into. Let's go with something fixed that basically makes everybody happy, kind of. Which I know you probably don't like that answer. I said I was going to make you sad. Okay. And so one particular thought is that you could take your image slicer and you just machine in different size slices. So some can be high resolution, nice thin slits that you can put over, say, a galaxy disk, and you get all the resolution you could ever want, whatever that is. And then as you move further out, you fatten those up a little bit. So now you've got a point where you've got your high resolution where you want it, but you've also got some field of view. So say you're looking at a diffuse gas further out, some CGM emission or something like that. You can collect a little bit more area, but you might lose maybe half your spectral resolution and a little bit of your imaging resolution as well. You can also do things like as soon as the light hits the image slicer, it's a separate channel. So the grading you could go to could be a near UV grading. It could be an optical grading. It could be an FUV grading, all in a fixed configuration. So you could have, in this case, I illustrated, half the slicers are going to FUV channels, half are going to NUV, all in one setup. Obviously, you'd have to spin around or move a little bit to get the whole field of view you want in 2 channels. But this is kind of just a way to think of how this could be architected. Okay, so what would I build if I was building one right now? And I'm going to start with the simple version, okay? So 1 detector for the FUV and maybe 1 for the NUV, different types, obviously. Fairly modest resolution, 5,000. Gives you the whole FUV bandpass and the whole NUV bandpass in one go. You don't run out of detectors or need to make giant tiles that might be kind of hard to control all your aberrations on. Half the light goes, down into one, half the light goes into the other. We've got different size slits for different size resolutions, and don't focus too much on the numbers. 50 milliarc seconds works great for me. I think that below 30 is going to be hard. Sorry. I just think if the telescope's making something like 15, there's going to be more aberrations built into that system that's going to make below 30 kind of hard. But hey, it's early, so we'll see what happens. And that leads to a certain number of gratings. Again, the little sounding rocket had 26, so going to 36 on a flagship is probably not too bad. The image slicer is fully buildable, and this would give you something like an 8x7 arcsecond field of view at this mix of resolutions. And then because I'm splitting in half between NUV and FUV, it splits in half. Or you can go crazy, and you can say, hey, we're going to have twice as many detectors. We're going to put the image slicers on a turret, which the ground does all the time. They're just basically fatter, so you can have thin ones or fat ones. I think JWST also has multiple modes. And all they're doing is changing in the slicer while the gratings all stay fixed. You could also, once the gratings are all aligned in their module, they become like an optic with just 36 different facets. So you could move that whole module. It's totally doable. So you could put those on a wheel, and you could have some medium resolution modes. You could have NUV and FUV separated. You can do all sorts of things. This is just showing you the scale range. And then you can get up to your larger fields of view or your higher resolution, smaller field of view modes. So that's all possible and all in range. And there's some talks I want to highlight of people who have been doing designs that are going to be on the last couple of days. The last thing I'm going to say is 15 minutes. We do need some technology development. We could probably build this with the detectors of today, but new ones are always better, so we should develop detectors. But the one thing I want to highlight that doesn't get a lot of attention is gratings, and specifically grating scatter. So there's a lot of engineering that goes into these gratings. but there's also grading scatter light in the far UV. And we know how much they scatter on HST COS, and it's not really a problem, except for maybe some science cases, because COS has such a small field of view and lets in so much geochronal Lyman alpha, so little. But as the field of view gets bigger, even though you're at L2, there's still interplanetary Lyman alpha. As the field gets bigger, this effect grows. And by my rough calculations, if you take the COS scatter function and you put it in the Habworld's IFS, it will be the dominant noise source. So it's not killing the science, but it's there, and it's something we're not really thinking about. So there's a lot of room for development there that we should think about. And I'll just end it there.
All right. Since I'm the chair of this session, I'm going to take the first question for Brian, which is we've seen some cases that want potentially higher spectral resolution. What do you think about that?
I mean, it comes down to the complexity and how much we're willing to scale this, right? So there's obviously a lot of spectral features people want, right? There's people who really want carbon-4. There's people who really want carbon-3 1900. There's people who want Lyman alpha. There's people who want 06. You make it high resolution, and you either need a meter of detector, or you only get a little bit of bandpass, right? And if you only have a little bit of bandpass, then you're going to make other people mad, right? Unless you put in a bunch of different modes, right? And so it's all a balancing act that's going to come down to how much are we willing to invest in this instrument. And remember, I came in with the, I'm going to convince you all. So I came in with the, I'm going to present something so simple, they're going to think it's free, right? So I haven't really been thinking that much about how complex we can make this, but it is possible, right? So that's just the balancing it has to go. It's the same with the field of view versus angular resolution trade. I mean, I'm not sure we're going to get to sub 10 milliarc seconds, but we could probably get a little range to 20, 30 at the current telescope designs. And that's great, but then the people who are like, but my galaxy's this big, are going to be sad.
Yeah.
So how do we balance all that is a good question.
Other questions? Yeah, in the front here.
Bertrand Menesson, JPL. Yeah, you're commenting about this. So it's both a comment and a question, I guess, which is that this trade between spectral resolution and field of view is one that we may have also for the coronagraph instrument and the IFS. So I feel like solving this problem here would also be relevant to the coronagraph side of things. Instead of having 10 by 10 arc second covered with 50 milli-arc second resolution, would be 10 times smaller in both directions. 1 by 1 arc second dark hole to be sampled at 5-6 milli-arc seconds. So that's great that actually both problems are about the same, and you could solve one, two birds with one stone here. Do you kind of agree?
Yeah, I do agree. I think in the coronagraph's case, there's room for a lot more optics. So for instance, STIS has great optical performance, great imaging performance. It makes a spectrum that looks the same no matter where in the slit you are, and it's about as tight as can get. But they do that with about 9 reflections. The coronagraph can afford 9 reflections, even in the near UV. Even with our new mirror coatings, the FUV telescope or instrument should not be doing that, right? It's going to have to allow things to get fuzzy and gross in certain areas in exchange for throughput, especially since the telescope's already throwing 4 bounces in. So
easier for the coronagraph than the far UV instrument.
Well, I don't think anything's easier for the coronagraph, but but okay, we'll say this one is. Yeah.
I think we have time for one more question. Steve.
Yeah, Steve McCandless, Johns Hopkins. Hi, Brian. Thanks for a nice talk. We've talked about this before, but can you explain the complications of maybe getting rid of all the gratings and just using one?
Yeah, that's how they do it on the ground. And there's so much aberration control that has to go into the gratings. And when you start talking about 50 or 60 beams converging into that one grating, it just kind of seems out of range. So I've tried that. I'm not an expert. I'm a very amateur ray tracer. And I find that it doesn't converge to a good solution in any kind of reasonable way. That said, when you go bigger, sometimes things get easier. So it is worth a shot. But it would end up being a big grating, which has its own complications. And maybe 60 small replicas of the same grating ends up being easier. So it's something that should be on the table, but I've found so far that it doesn't work very well. Not without a bunch of controlling for optics, and there's your throughput just going out.
All right, thank you. And our last talk before lunch, and as a reminder, directly after this talk, are people sitting in the chairs or are they coming up here? So all of you at the back have to come to the front for the picture so that 30 years from now, you can see your face. And people who are upstairs in the overflow room, please come down for the picture. Okay, be in the picture. So our last talk of the session is gonna be Shouleh Nikzad from JPL.
Thank you. Thank you, Erika. Can you hear me? My microphone works? Thank you. And I thank Janice and the organizers for this fantastic conference and for inviting me to tell you about the exciting technologies that we are developing for ultraviolet science instruments in HWO. We've been hearing for a day and a half about this exquisite observatory with great capabilities that's hopefully is going to go up, and we'll get all the science back from it. We've been lead, and Paul talked about the instruments that are notionally designed for this, and we're going to have a lot of capabilities coming to the focal plane, which is part of what I'm going to be focusing on. We also heard a lot of science cases that comes through UV observation. I like this visual because it shows how many spectral lines we have in this range that is going to lead to the type of information that we've been hearing in the science cases, the lava world, the heavy metals, the understanding the atmospheres. All of those things are going to be gathering information, gathering a lot of photons through different channels, this big aperture, even though Jason and Heidi are not going to get their 40 meter, still 6 to 8 meter telescope is going to gather a lot of photons, and through these instruments is going to land on these detectors. I'm going to focus on detectors, a little bit on coatings, and some mention of gratings. And partially I'm focusing on detectors because that's the major part of what I do, but also because how much their parameters, their performance is going to impact the discovery and science return. When you have really low noise detectors, the SNR of the detector has direct impact on the SNR of observation. And how many faint objects can you see? Farther distance objects you can see. The enhancement of the discovery is going to be improved. So this is an area that is going to be really important to make sure that we have the right detectors with the right performance, and while we are keeping an eye on the cost and schedule, the maturation process. And the good news is, as Paul was mentioning, everything that I will talk about today is TRL 3+, in fact 4+, in some cases 5+. So it's not like we are at the invention or even at the innovation part. We are very close to infusion. We have to close the gap and get those into this observatory. Similarly, for coatings and gradings, similar comments could be made about those. And Brian just talked about the low scatter that we would like, the high efficiency that we would want from gratings. So I will talk about coatings as far as they are relevant to detectors, and I will mention them on the optics as well, and a brief mention of gratings. And I'm also further going to focus on silicon detectors. Reach into your pockets, into work bags. What will you find? A silicon image sensor embedded in your smartphone, in your laptop, in your iPad. And that is the kind of billion-dollar industry that starts from sand and makes this defect-free material that we can make great detectors out of. And it's a very attractive industry to leverage from. We can get those images into scientific capability and get great discoveries happening. And that leveraging happens if you collaborate with them, because their roadmap will diverge from what we need. So, but collaboration and focusing them on the goals of space applications and scientific applications is what will give us the leverage that we need. There's also leverage from everything that we've learned from working on silicon detectors in astronomy. Everyone in this room knows what CCDs have done for astronomy. With their linear response, with their uniformity, the sensitivity, they made those beautiful images out of the Wide Field Planetary Camera and the Hubble Space Telescope. Sean talked about how great these images are as ambassadors of the type of things that we do with these telescopes on orbit, but also the discoveries that have been enabled by that. Their photometric stability has made Kepler and discovery of exoplanets possible. And then their manufacturability and scalability has made these near gigapixel and gigapixel focal plane of Gaia and Euclid possible. So that's just one axis of how silicon detectors have improved and have grown. There are other axes that is not evolutionary, rather revolutionary. Right about the time that CCDs were going into Hubble Space Telescope, first CMOS image sensors were being developed. And while they had some really attractive features with their parallel readouts so that they didn't need to transfer charge as many times, be more radiation tolerant, maybe more space friendly, region of interest readout, maybe faster readout for, we were talking yesterday about tracking objects and tracking events. But they were not yet scientific detectors. They had a little bit higher noise, but I will show that they have improved a lot. CCDs haven't stood still. We have now EM CCDs that have been delivered to CGI, Roman CGI. Photon counting has become possible. The low noise CMOS has become possible. So it's a very exciting field and in all sorts of dimensions that have improved and has grown. And I'm going to talk about photon counting in silicon. Paul talked about we need photon counting. And in both the IFU that we were talking about and potentially coronagraph and UV instrument, we will have the need for photon counting detectors. And the good news is that photon counting is possible in silicon. The way you do it, you increase the SNR either by amplifying the signal and or by suppressing the noise. And these two large categories, I'm showing two examples of them here, EMCCDs and avalanche photodiode arrays. And in the suppression of noise, quantum image sensor invented by Eric Fossum at Dartmouth, and now GigaJot is making them, and Hamamatsu has the QCMOS. And actually, I have a student of Eric's doing his thesis with me, and getting QIS maybe further for back illumination and maybe UV response. We also have Skipper CCD and CMOS. Erika and I have an SAT, and we also are part of a bigger collaboration, foundation funded, that is trying to make these Skipper CCDs with the readout speed that is more practical, and we can use them for astronomy, maybe increasing the number of readouts. And Nathan Bush and I have a little bit of funding to look at the CMOS version of these. So there's a lot that is happening in the photon counting, in the readout, and in the format increase, and all the good stuff that you need for your instruments. Okay, so that's where it comes to maybe visible. How do you make this UV sensitive? Without getting into a lot of details of the physics of the challenges of ultraviolet detection, I will just remind everyone that ultraviolet is absorbed in the first few nanometer of material. So if you want to get those photoelectrons that are produced by, or photocharge that is produced by UV photons, you need to have a good electronic structure at the nanoscale of the surface. And that's what we've been doing. We've developed this over the years. We do two-dimensional doping, delta doping, using molecular beam epitaxy. And about 15 years ago, JPL made an investment of a first-of-its-kind machine, the silicon molecular beam epitaxy, that is capable of processing 8-inch wafers. So that it satiates the appetite of having bigger and bigger detectors, but it's also doing batch processing of multiple of those detectors. So you could line big focal plane arrays with these in a cost and schedule that is reasonable. But it's also compatible with the foundries of silicon fabrication. And that's really important because remember I said we need to leverage from what the industry does and all the innovations that are coming along. So we need to be compatible with them. And the way we have done this with the processes that we have developed makes us agnostic to the architecture design, the pixel design. So that means that we can take any foundry's wafer and put it through our process and make a UV version of it, or very stable, high quantum efficiency of visible or ultraviolet, depending on the coatings that we will do on this. Now, the agnostic aspect, I'm going to just show some examples of a handful of different devices. The photos of those shows regular CCD, even a Cassini CCD, EM CCD, P-channel CCDs that are a little bit more radiation tolerant, deep depletion CCDs that are going to give us the near infrared response as well. And on top, I'm showing the quantum efficiencies that we have achieved with these and other devices. There's a CMOS one on the far right that you will hear in Kevin France's presentation on Wednesday. The 2D doping, the nanoscale engineering that we do with MBE, gives you 100% internal quantum efficiency, which means you're limited by reflection only. Now we use atomic layer deposition to make these custom coatings and tailor the response that we want. And here I'm showing some that are 60%, 80%, 90%, depending on the range that we were designing these for. And that's been, ALD actually has been a real godsend because of its atomic layer by atomic layer control and having scalability, arbitrarily scalability to larger arrays is a really useful tool, and we have put it in really good use. In fact, it has also enabled other innovations that I will get to in a minute, but the tailorability that I was talking about with using the coding can also be done in terms of the spatial definition of the areas that we want to maybe enhance or suppress a certain part of light. April Jewell and I believe Erika and the team worked on making these block filters and block coatings on a device here. It's actually an EMCCD and showing the enhancement of the different regions for different wavelengths. The breakthrough that I was talking about, using also partially enhanced by or enabled by ALD, is putting metal dielectric filters as an integral part of the detector. So now you can get this detector that was a very strong UV and visible detector and suppress the out of band or suppress the visible and get a solar blind or visible blind detector. These are two really amazing and breakthrough development with the photon counting, with the solar blindness. And remember, the scalability and manufacturability is still there, reliability is still there. So this is a very exciting development. For Sparks, I see Evgenia sitting here as the PI of Sparks. We developed a 2-channel camera and delivered that. Hopefully Sparks will be launched soon. And we used these filters that originally they were actually developed for a DOE project, Department of Energy project, but we really honed on this and made it for the far UV detector of Sparks. And now for the UVAX, which is the current MIDEX in phase B, we are developing those filter for the long slit spectrometer with a graded profile. John Hennessy has done a really nice job of making this work to get nice in-band efficiency and some suppression of the scatter. I talked about collaboration with industry and focusing them on what we need. EMCCDs were developed for bio applications, not for space applications, not for astrophysics. But they had a potential there for these applications. So we started working with E2V. Chris Martin actually had an idea for SMEX. And seeing that our capability was A, compatible with their fabrication, and B, was enhancing, giving them capabilities they didn't have, we started working together. And here is showing the fireball conglomerate of the data and some of the photos of the flights. We had 2 flights. Although we had balloon problems, Gillian Kine, who was the lead for the detector system, had the presence of mind to check off all the detector capabilities. And those nice 80% quantum efficiency that you see is a multi-layer ALD coding. So this is an example of both working with industry and getting most out of those silicon detectors that they've been developing maybe for something else, but also working with academia where we could get these suborbital tech development and tech demonstrations, and also working with the next generation of leaders. And some of them are in this room right now. I mentioned sparks and the delivery of those. This is another example of working with academia and getting access to space as a small sat, both showing the feasibility of the science, demonstration of the technology, as well as getting the next leaders developed through this process. The codings that I mentioned, they are for detectors, but I'd be remiss if not mentioning that it was not lost on us that it could be protective codings for mirrors as well. And that's what John Hennessy has been doing with Brian Fleming and Kevin France and on rockets and small sat demonstration. And with Goddard, it's, you could either use ALD entirely for the coding or with the combination with the process that Goddard has developed. I already mentioned UVEX. I'll just say that this is CMOS with SRI collaboration, 300 megapixels of these. And we also have the long slit spectrometer that has about 33 megapixel as well. There is a roadmap for getting deep sub-electron noise in CMOS, and that's a close collaboration with Teledyne E2V. Michael Hoying, Kevin France, and David Shimonovich are close collaborations on this. And I will just show that the gratings that have low scatter and high efficiency that Dan Wilson et al. Have been developing and deploying for over 22 years on short wavelength IR and visible and a little bit of near UV is now being focused on the ultraviolet. We delivered to Sherlock grating, which was flat, and Dan has also made 2 for our Offner Aves spectrometer, which is for planetary applications. And I will leave you with this thought, showing an arc of development of one of our technologies, and paraphrase, like I have done before, one of our national heroes, that the arc of technology development is long, but it bends towards success. Only if you have good technologies, perseverance, a good science motivation, a mission that's waiting for it, and the investment that is necessary. And we have that in the cusp of the HW. We have all of those elements, and I'm really excited to be part of this community. Thank you.
Okay, we have time for just a couple of questions for Shouleh. Any questions? Oh.
Hello. Thanks, Shouleh. Brian Fleming, I just talked. I've been really obsessed for the last 2 months with gratings, and I know, you mentioned that just a little bit, but it's the conventional wisdom that holographic gratings are what you use in the UV. It's what was used on COS. It was what was used on Fuse because of their excellent scatter performance. But I've learned very recently that it's not good enough to be inconsequential on HAB worlds for the MOS or the IFS. It's a new discovery for me. So when you say very low scatter, do you know if there's a measurement? Is there a comparison to the state of the art on those?
We are working on getting those UV, those measurements of the scatter in the UV that we needed to have the right setup, because Dan had those for visible and short wavelength IR. I can get you those numbers once we have them. But they've performed really well in those other wavelengths.
UV is really different. But yeah, that'd be great.
Yeah, you don't need to tell her that.
Yeah.
And other questions? Oh, here in the front.
Thank you. So I had two small questions. One is, what are typical costs for either delta doping, ALD, or 2D doping? And then for CMOS detectors, is there a preference for delta doping or 2D doping?
Oh, 2D doping is a general, let me just address that. 2D doping is a general term that we talk about either delta doping or superlattice doping. Superlattice doping is the multi-delta layers, and I can tell you in more detail offline about why we choose one or the other. But the cost of the delta doping and 2D doping is the same. And I don't want to get into the giving you a cost, but that's something that we could talk offline. But it's not something that adds a lot to the cost of the detector. I mean, we've proposed those for missions and UVAX won, so it was reasonable cost.
The hard part is getting the detector out of Teledyne. Okay, so thank you to Shouleh and thank you to all of our speakers from this session.
So an announcement from Janice, please everybody come down here. For the picture, you cannot be in the boxes and everybody needs to be standing. Please fill every seat. So if you're already down here, move to the center.